Hi, this is Greg. I want to go ahead and finish up the water unit. I talked about Module 41 earlier, and we're going to finish up the rest of that chapter. So Module 42 talks about heavy metals, and we see those with mining and with burning fossil fuels. The example here we have is mercury. Now, the primary source of mercury, as far as air pollution or water pollution, is from burning fossil fuels. There's also a minor component with this artisanal mining, where they're using mercury in order to pull gold out of ore. That is a problem in some lesser developed countries. And there's an example there. You can see the mercury here. Okay, on to different types of heavy metals. Lead is one. It usually does not occur naturally in drinking water, but it can come out of the plumbing that you find in older homes. It is a neurotoxin, so it interferes with brain development. You need to be familiar with the case study with Flint, Michigan. So originally, Flint, Michigan bought its water from Detroit, and Detroit's water was treated with something called orthophosphate. And that particular chemical would form a layer, a protective layer on the inside of the iron pipes and the lead pipes that would protect it from corroding. This picture here, the white stuff here, protective layer. What happened was Flint decided they would save money. The water that was coming from Detroit was expensive, so they wanted to save money. They pulled the water directly out of the Flint River, which for one had higher chloride levels, which is corrosive to pipes, and also it was not treated with the orthophosphate chemical to coat and protect the pipes. So what happened was that chloride helped to degrade that protective coating that was there anyway, and then we had no more orthophosphate in the water to add to that coating. So then we had lead leaching out of pipes. We had iron oxidizing, making the water rusty as well. The lead concentrations were extremely high. You start worrying about your health with little children at levels of 5 parts per billion. Some water was tested to be as high as 13,000 parts per billion. So there are going to definitely be long-term neurological effects there. Moving on with the heavy metals, arsenic, that naturally occurs in the Earth's crust, and you can find it in groundwater. There are certain places over the Earth where we see more cases of arsenic than others. For example, I know in India there was a problem with the groundwater was contaminated. So what they chose to do was to dig deeper wells in order to access water that had not been contaminated. When they did that, they ended up tapping into groundwater that was contaminated with arsenic instead. And so there are lots of people in that region that have been affected by arsenic poisoning. But arsenic is naturally over several different areas. You can see there's arsenic that naturally occurs in the United States, but it is poisonous. And then a little bit more about mercury. So again, the primary source is burning of coal. I've taught in class before about Minamata disease, named for the city in Japan where the cats were eating fish that had been poisoned with mercury. And the cats first showed, they called them the dancing cats of Minamata. The cats first showed neurological distress as a result of mercury poisoning. And then a year or two later, this happened in the 50s, a year or two later, the people started showing problems with mercury poisoning. And it's not the mercury itself. When the mercury itself gets into the water, what happens is that bacteria will convert that mercury into something called methylmercury, which is then taken up by living organisms, and that's what's toxic, is the methylmercury. And as far as who contributes to mercury in the air and in the water now, it's mostly Asia, as they become more and more industrialized and don't have the same types of pollution controls that other countries may have. And then just an example with how the mercury poisoning works. You end up with mercury in the air as a result of burning coal. Mercury then goes into the water. The bacteria in the water convert that mercury into methylmercury, which can be taken up by other organisms. You start low on the food chain with phytoplankton and zooplankton absorbing that methylmercury, and then you have the fish that come along and eat. And as we move up the trophic levels in that food chain, we see there's not only bioaccumulation in the individual organisms at each trophic level, you see a magnification as we move up higher in the trophic level, where those top level predators, from eating all of the organisms that are underneath in the food chain underneath them, they end up with extremely high levels of mercury. So there's bioaccumulation and biomagnification again. Those top level predators, those fish, there can be so much mercury in those that there are warnings for pregnant women not to consume them. So things like It used to be tuna. I noticed that tuna is off the list now. But swordfish, shark, king mackerel, tilefish, those things, if you were pregnant or nursing, you would limit that to just a couple of times a week because you would not want to expose your unborn baby or your nursing baby to high levels of mercury. And DDT, be familiar with that. As far as eggshell thinning, we saw problems with eagles as DDT biomagnified up the food chain with eagles. There are lots of things that will bioaccumulate and biomagnify. DDT, mercury are two examples, also PCBs, things that were used. They're fireproof and they're used in transformers. Those are endocrine disruptors. Those will also bioaccumulate. And by bioaccumulation, that means that they're going to stick around in the fatty tissues. So they hang around in the fat. They aren't water soluble. If it were water soluble, then that would pass right through an organism in its urine, in its own urine. But with fat soluble things, that accumulates in the fatty tissues and it does not go out of the organism. That's how it bioaccumulates. On to acid deposition. Things like NOx, SOx, as that goes into the atmosphere, we're going to cause basically sulfuric acid, nitric acid to rain down. And then what happens there is that we're going to leach things like aluminum ions out of the soil into the water. Those aluminum ions are toxic to anything that's living. Nothing can tolerate much in the way of aluminum ions. Moving on to acid mine drainage, we talked about this whenever we did mining. So pyrite, which is iron sulfide, when it is exposed to water, say underground mines that fill up, they're flooded with water, and then also exposed to air, then we end up making basically sulfuric acid. Whenever you see a stream that's been affected by acid mine drainage, it tends to be red because of the iron that will precipitate out into that stream. And then there are all kinds of different synthetic compounds that we are exposed to, things such as pesticides, pharmaceuticals that we take. There are certain military compounds and industrial compounds that are used. All of these can cause problems. And there can either be point sources or non-point sources, depending on what we're talking about. Endocrine disruptors, those are things that can mimic hormones or interfere with hormone functioning in an individual's body. Endocrine disruptors can cause birth defects, developmental disorders. We saw with the Chesapeake Bay case study, there were gender imbalances in the fish. There were problems with male fish producing eggs like a female. And then on to pesticides. DDT is a famous one. Again, that's the one that caused the eagles to have the thinning shells. It was used to kill mosquitoes. It was very effective for that, but as it bioaccumulated and biomagnified up the food chain, it severely affected the eagles. And that one was banned in 1972, and it took a while for the eagles to recover. By 2007, they were off the endangered list. Persistent organic pollutants are synthetic. They are carbon-based, hence the organic thing in there, and then they're persistent. They stay around in the environment a long time before they break down. There are all kinds of POPs, pesticides, different solvents, pharmaceuticals, industrial chemicals. Key examples you need to be familiar with: dioxins, DDT, and PCBs. Those are all examples of POPs. They happen to be fat soluble, means that they're going to stick around in the fatty tissues, means that they can bioaccumulate and then biomagnify up the food chain. Also, they will volatilize pretty easily. So they will go into the air and then they can be blown long distances. So maybe the local area where you live, those particular persistent organic pollutants weren't used, but they have traveled long distances now from some place, and now they have landed where you are. So they can travel long distances on the wind, and you can find them in soils, vegetation, and water. Some examples: Agent Orange, that was used in Vietnam to defoliate. That's an example of a persistent organic pollutant. Dioxin, which is a part of Agent Orange. There was a famous place called Times Beach, Missouri, that is contaminated with dioxin. It's been cleaned up now, but in the 70s it was contaminated with dioxin because there was an Agent Orange manufacturing plant that had leftovers, and someone said that they were going to spray the dirt roads with oil, which is a common practice. in order to keep the dust down, but instead of spraying with oil, they sprayed with leftover stuff from that dioxin factory and ended up spraying dioxin all over the roads and contaminated that area. PCBs, they were used in the manufacture of transformers. They're very heat resistant. Those things are persistent. And then DDT that we've talked about in the past, they're spraying it for mosquitoes. Pharmaceuticals and hormones, they cannot be removed by a wastewater treatment plant. So all of those pills that people take, and so we excrete hormones just naturally anyway, all of that stuff goes out into the local bodies of water. So things like birth control pills that women take, different types of hormones that people may take, all of that can be excreted in small amounts in your urine, and it winds up out in a body of water. There's some other chemical pollutants you need to be familiar with. MTBE is it was a gasoline additive. After we outlawed lead as a gas additive for an octane booster, we switched to MTBE. The problem there is that it can leak into the groundwater from underground storage tanks. It's not thought to be dangerous, although they're looking into it as a potential carcinogen. It's not confirmed. The problem, though, with the MTBE is that it makes the water taste bad, and it's hard to get that out of the water and clean it up and make it taste better. Also imparts a smell. There are PFCs, and some examples are something called PFOA that was found in Teflon that was used in the nonstick cookware. And then there are stain-resistant things like Scotchgard that you can spray. You can cause, like if you spray it on a fabric sofa or on a jacket, it will make it repel water, so that way it resists staining, and that's caused by something called the PFOS. Those two things, those PFCs, those will affect hormones. They're an endocrine disruptor. They also cause problems with immune systems. These things are fat soluble. They will bioaccumulate. And then there are flame retardants, PBDEs, that were put in sofa cushions and various electronics, clothing. There would be baby clothes with flame retardants in them. And all of those are also endocrine disruptors, and they can affect the development of fetuses. Then there are perchlorates. That's one of the industrial ones. It was used in rocket fuel. That one is also persistent, and that will contaminate food and water supplies. It is an endocrine disruptor. Some case studies you need to be familiar with. The Hudson River is a PCB Superfund site. So the General Electric Company, they made capacitors to use probably like in transformers and various electrical equipment, and they discharged excess PCBs into the river. Those PCBs, they aren't necessarily water soluble. They will settle down and get caught in the sediment on the bottom of the river. So the EPA has had to dredge all of that sediment to remove those contaminants so that we can clean up the river and clean up, it's one of those persistent things. So there are PCB contaminated fish. It's going to take a while to remediate that. And then there is the river in Ohio, which I am probably going to murder the name of that. I'm going with Cuyahoga. That one was polluted for a long time. For over 100 years, industry would dump extra chemicals into that river. It had a permanent oil slick on top of it, and it caught fire a bunch of times. But in 1969 was the one that helped spur the American environmental movement. It was on the cover of Time magazine, and this prompted the establishment of the EPA, and it also pushed us towards the Clean Water Act. And there's a picture. This is what it used to look like. Here it is on fire, and it's cleaned up now. All right, on to oil pollution. So we get oil pollution as a result of tanker accidents, the big tanker ships that transport oil. If they have an accident, they're spilling oil. Also, you can have offshore drilling rigs that can put out oil pollution. And then there's some natural seeps. It doesn't all have to be man-made. There are natural areas at the bottom of the ocean that are just seeping oil. And then the problem with oil is that we end up with organisms coated in oil. It makes it difficult for them to swim. It's also toxic to them. Also, the problem with that is that we end up with economic consequences. This is a picture of Pensacola Beach after the Deepwater Horizon. The beach was all covered in oil. It took a while to clean up. You're losing that tourism. You're also losing the fishing industry temporarily. Some of that oil has settled on the bottom of the ocean, so it interferes with the growth of those bottom-dwelling organisms. This shows a coral that's covered in oil, and there you can see there's a red brittle star that's clinging to it. How do we clean up oil spills? There are a couple of ways. One is you can have a floating boom that will help to contain the oil spill to keep it from spreading any further. Then we can have skimmer boats that come along with these skimmers, and they will vacuum up the oil as it has been contained, and they'll collect it. And then if you're close to the beach, they may put out absorbent pads in order to help absorb that oil before it reaches the shore. There are chemical methods of controlling oil spills. There are coagulating agents that you can spray into the water, and it will help the oil to clump together, and it will sink to the bottom where it'll do less harm than floating on the surface, where it will be coating those organisms like birds that are on the surface. And also makes it easier to pick it up. If you've clumped that oil together, it makes it easier to collect. Then there are things called dispersing agents, and that will break up an oil slick. So here you see a plane flying and spreading a dispersing agent. And the idea there is that it will make the oil leave the surface where it can cause the most damage to organisms, and it will sink deeper in the water column. Also, if you're breaking up those particles into teeny tiny bits, it's going to make it easier for the oil to degrade faster. Another way that they take care of oil spills is just to burn it off, but the problem there is that we're putting tons of pollution into the air, and then we're also going to harm aquatic life with the sludge that's going to be left over floating on the surface. So that sludge can be even worse than the oil. There's natural action that will happen to degrade the oil. So as the wind and waves, you get that action, it helps to mix up the oil and get it off the surface and disperse it deeper down into the water column. Also, there are natural bacteria that exist in the water, and they will degrade that oil. As far as underwater oil plumes, where we have seeps, or if we have a leaking underwater rig, there is no way currently to take care of those underwater oil plumes. They're investigating ways to take care of that. You can take care of it on the surface, but it's hard to take care of it underground. You have to stop the leak. Or under the water, you have to stop the leak. Be familiar with the Deepwater Horizon rig that had the explosion in the Gulf of Mexico in 2010, and also the Exxon Valdez tanker that was in 1989, where one of these it was a big tanker ship. It ran aground, spilled oil everywhere. We had lots of creatures that were covered in oil. The entire coastline was covered in oil, and that was a big cleanup and recovery effort. Okay, on to non-chemical water pollution. Here we've got solid waste going into water. United States, we used to practice dumping garbage in the ocean, but then we have stopped that as of the 80s. But there are still plenty of countries that dump their garbage into the ocean. And here's a picture in Indonesia with a river filled with garbage. Also, another problem as far as solid waste and dealing with water pollution, we've talked about coal-fired power plants and the ash that's left over that's stored in ash ponds. So that can leach into the groundwater and contaminate groundwater. As far as ocean pollution, 20% of it comes from marine sources. So fishermen, nets, ropes, lines, they're losing some of that in the ocean. That's what 20% of the plastic is. And the rest of it comes from terrestrial sources. If you throw something out in the street, washes out through the sewer into the nearest body of water, which then rides out and dumps out into the ocean, that's one way that we get terrestrial sources. There are 6 countries that contribute to most of the plastic in the ocean, and those 6 are over in Asia. And these are pictures of plastic pollution. This is a river that's covered in plastic. And then the problem with plastic is that you can end up blocking the intestines of creatures, becomes choking hazards for them. I'm sure you've seen the pictures of the animals with the 6-pack rings around their necks. Also, you get microplastics, teeny tiny, that get ingested, and then those plastics can move right on up the food chain. We're all probably eating plastic and also breathing in plastic at this point. And then again, as far as mismanaged plastic and where the plastic is coming from, the biggest source of all that plastic comes from Asia and the Pacific. And then you watched a video about some of these gyres, there's the North Pacific Gyre, where we have the Pacific garbage patch. And they've talked about it being larger than Texas. And it's full of garbage. And we're not talking about necessarily huge chunks of garbage. It can be small microplastics. After that plastic's been sitting out degrading and being broken down by wave action and ultraviolet light, we end up with just small, teeny tiny bits of plastic that can be eaten by organisms or mistaken, they mistake it for food and eat it. So like I said, we're all eating plastics. Let's see. Microbeads were outlawed in the United States. They used to be in cosmetics, little teeny tiny plastic beads that were used maybe like in face scrubs. That's been banned now, so they have to be natural beads, not artificial beads. So that's helped as far as microplastic pollution. And then as far as other pollutants, sediment, suspended matter, whenever there's erosion and we're washing in dirt into a local body of water, then we end up reducing the amount of light that can filter in, and we end up lowering the primary productivity of that body of water. Whatever green things are on the bottom of that body of water are no longer able to photosynthesize and put dissolved oxygen into the water. Also, that sediment can clog the gills of fish and things like mussels or clams that live in the water. So that can totally disrupt food webs, that lack of dissolved oxygen, and also the fact that you're killing off, basically suffocating creatures with sediment. And then as far as inorganic nutrients, we've talked before about excess nitrates and phosphates. If you over-fertilize something, then that fertilizer can wash into the nearest body of water, and you end up with an overgrowth of algae like you see here. And then as those algae die, then the microbes are going to be depleting the dissolved oxygen. We can end up with things like fish kills as a result of that. Also, we can have disease-causing agents. You'll learn more about the different types of diseases in Chapter 17, but those can also be waterborne, some of them. And these are some of the waterborne disease-causing agents that you need to be familiar with. But the big ones are covered in the Human Health and Toxicology presentation. Just kind of scan through these, but be familiar with the ones that are specifically in that Human Health presentation. And then also there's thermal pollution. So anywhere industry, particularly power plants, are using lots of water for cooling. It used to be that it would be a once-through process. So they would use it to cool down machinery and then dump it into the local body of water, and they dump it out hot. They wouldn't cool it down first. That hot water, whenever it goes into the river, it will, for one, deplete the dissolved oxygen in the river because warm water cannot hold as much oxygen as cold water can. And also there's thermal shock to the fish as that hot water is released in. You can't dump hot water on fish and expect them to fare well. They need pretty even temperatures. And then here's an example of thermal pollution. This is, there's a particular bay, this satellite photography shows a particular bay in China, and you can see where there are 2 power plants here. And then you can see the thermal pollution as a result of them dumping cooling water out into the bay, and you can see how far that extends. And then the solution there is not to use your cooling water as a once-through process, to recycle that cooling water and use cooling towers in order to cool it down before you send it back into the process to cool machinery. And some other sources of thermal pollution, as we deforest and we're moving the shade that's over bodies of water, that increases the water temperature. As we have runoff over hot pavement in urban areas, you're going to end up, that warm water is going to run off into the nearest body of water and cause the temperature to go up. Also sedimentation. Cloudy water is going to absorb more light than clear water, and it just makes it warmer. And then again, the effects of thermal pollution, you're going to have lower DO levels and thermal shock to the organisms that live in that water. Then there's noise pollution. So noise pollution can be so loud that it will disrupt marine organisms' ability to communicate with each other. Y'all have looked at noise pollution before, and you've looked at some of this in detail, but some of the examples with whales, that it interferes with the sonar on ships can interfere with whales and their communications over long distances. I should be familiar with those. And then we have the range of tolerance that we have looked at in the past, that there's an optimum range where organisms can live. And then as we get to the extremes of that range of tolerance, organisms begin to suffer. Okay, so within that zone of tolerance, within that optimum zone, organisms are able to maintain homeostasis and keep their body functions pretty stable. But once they get outside of that, you can have a zone of physiological stress where you still have organisms that can survive there, but they just aren't faring well. They aren't able to reproduce at the rates that they need to. They're just having a hard time. They're struggling. And then you can get all the way out to a zone of intolerance where nothing is able to live. We end up killing off organisms. So just be familiar with that again. We've studied that before. Coral reefs. This is coming straight from the AP material. They're featuring this. So the coral reefs, as we have seen a rise in ocean temperature, we're seeing the coral reefs die off. For one, it causes coral reefs actually have a symbiotic relationship with algae. So as the temperature of the water rises, it causes the coral to expel the algae. And without the algae, it has to have that symbiotic relationship with the algae. It loses its color for one, and then also without that algae and that symbiotic relationship, that coral will die. That's one reason for coral reef die-off. Another, as we send sedimentation into the ocean, it literally smothers the reef. And then also, as we have seen pH changes, that's not on here, as we've seen ocean acidification, that has also contributed to some of this expelling the algae and seeing coral bleaching happen. Be familiar with wetlands. We talked about this at the very beginning of the course, and all the different ecological services that wetlands provide, such as water purification, flood protection, water filtration, and habitat for certain organisms. Be familiar with mangroves, and that as human development encroaches on them, we are removing those mangroves. For dam construction, we are developing along the coastline. We're having, houses and stuff along the coastline, and so we're removing some of that natural wetland area that we need. And we benefit from that in that they will remove some of those pollutants that we end up putting out as a result of agriculture and industry. All right, on to the last little bit. Be familiar with the Clean Water Act. That's one that you need to know. We covered that back with the legislation, so I won't review that. You can review that. Also, the Safe Drinking Water Act. Those are two that are specifically called out by AP that you need to know. The Safe Drinking Water Act is going to establish these maximum contaminant levels for 77 different substances. And then here we have an example of the maximum contaminant levels. This is what they're going to measure in our drinking water to make sure that our drinking water is safe. And then what are some future solutions, some green ways to make sure that we have clean water? One, with wastewater, like with sewage, you can use things like microbes, algae, plants, snails, and a man-made wetland in order to clean up water. If we're talking about preventing erosion and preventing runoff and so forth, we can have rain gardens, which is good if you have a soggy area anyway. Plant something that's going to be tolerant of that water and will be able to absorb that water and handle it and prevent runoff. Bioswales is another way to handle runoff. This shows you've got a bunch of rocks and some screen over it to keep it from moving. But as you get a lot of rain, it allows that water to seep in and flow without causing erosion here. And then here's another example of a bioswale where we have trees growing in. Green roofs, we talked about those before. And that's it. Wow, almost 30 minutes. Sorry. Hope that helps, and I will see you next time.